Welcome back, everyone. Thank you for joining me for this session. My name is Nadia, and I'm a software engineer at Facebook, and I'm working on automated testing. I have been at Facebook for about 3 years now, and before that, I worked in different banks, and I also worked as a researcher for a long time on automated testing. Today, I'm happy to tell you about how we are at Facebook improving the quality of our apps using a new system we call Virtual Alpha. So one of the worst experiences a user can have is something like this. So you see this message on the screen. We've all been through a situation like this. You're in the middle of something. For example, you're creating a post or writing a response to someone, or you're trying to upload your holiday photos. You spend so much time writing your comments, adding your tags and photos, and then suddenly something goes wrong and the app crashes and you have to start all over again. This is very frustrating and a negative experience for our users. And it's something we really want to avoid as much as possible. Because of this, we developed something called Sapiens. So you can, and we do at Facebook, write manual tests, end-to-end tests that test the different flows in the app, but you can't cover every possible flow with manual tests. And there will always be something, an unexpected combination of actions that you missed. So for this reason, we developed Sapiens. Sapiens is an automated exploration tool. I talked about it in an early version of, I talked about an early version of Sapiens in a previous TEQnation in detail. So like I said, Sapiens is an automated UI exploration tool that is completely and fully automated. No one writes the tests. It uses different algorithms to use the app in different ways and try to crash it. So like I said, no one has to write the tests, and you can, the flows through the app that you can cover are infinite, because every run of Sapiens leads to a different sequence of actions that explore the app in a different way. So we embedded Sapiens in the continuous integration process at Facebook. Once an engineer submits a diff for review, and while the review process is going on and the engineer is waiting for the results of that, the CI system creates a build of the app with the changes that are in the diff included in this build. Sapiens will automatically pick up this build and run multiple tests. If Sapiens finds a crash that is related to the changes in the diff, it will comment on the diff with details about the crash. So it will include all the logs from the device, it will include the video, and it will also include the stack trace and all the details about the test user that was used and their configuration. For us, this has been very effective because engineers usually respond very well to this, and most of the time they do fix the crash before landing the change. Sapiens started on the Facebook app for Android, and once we felt like we reached a good level of maturity on the Facebook app, we expanded to run on most of our major apps. So we run on Messenger, on Instagram, we run on WhatsApp and Workplace, and we also run on Ads Manager. So for most of these, we also run on the iOS version, and for some of these apps, we also run on the web version, like, for example, Facebook and Workplace and Ads Manager. Especially Ads Manager, we are very mature on running on the web version because it's much more, it has a lot more features. Okay, so how does Sapiens work? How does the algorithm work? So the first thing that happens is that Sapiens will install the app on an emulator and then will open it and log in. So that's the first thing that will happen. And then it will wait for the app to respond. It will look at the screen, detect all the possible actions on the screen, and then start building a graph of those actions and how they relate to each other. So for example, on this screen, we have 3 actions. So we will start building a graph with these 3 actions, as you can see on the right side of the screen. Sapiens will then score the actions on the screen and rank them, and then execute the highest ranked action. The ranking algorithm is completely pluggable and can be anything you want it to be. For example, we use an algorithm for diff testing that tries to maximize coverage of the UI actions. So basically, we explore the app and we try to find as many actions as possible, and then we try to cover all of them. So at every step, Sapiens will rank the actions on the screen and execute the highest, like I said. Ranked action, and then continue to build the graph on the right using the information in the future for scoring. So here, to start with, the scores would be all the same because we don't have any information about these actions. So we would just pick one randomly. So for example, let's say we picked the first action. This led us to when we click on this action 1, we will see this new screen with 2 new actions. So we add them to the graph and rank them as well. We still have no information about the actions on this screen, so we will still pick randomly. But let's say we picked action 4. If we ever came back to the screen again and using our algorithm of trying to maximize coverage, then 5 would rank higher than 4 because 4, we already clicked it. So if we click it, we wouldn't increase coverage of the UI actions. So then, of course, 5 would have a higher rank. But let's say the algorithm was trying to trigger actions that use the cache, for example, then 4 would rank higher than 5 because it was executed before. So it's more likely if you click it that it would trigger something to be retrieved from the cache compared to action 5, which is new. So it will most likely go to fetch from the network. So the algorithm continues ranking and building the graph. And once, let's say, for example, we are in this situation where all the actions have been executed at least once, except for one. As you can see, there's the dark red one in the middle of the graph that hasn't been executed. And let's say we are back at this screen, the first screen with the 3 actions. Now, they have all been executed, so there's no immediate benefit of clicking any of them. But then the highest ranked one in this case would be action 2, which is the yellow action. And the reason for this is because it is the first step on the shortest path to the closest unexecuted action, which is the red action. So if we take any other path, it would be a longer path to this unexecuted action. So this is how we would prioritize. Okay, so Sapiens runs on every diff for the apps we support, but it also runs on master. And the reason we run on master is that we want to flag any crashes that somehow made it to master. For example, because the engineer did not fix them or because Sapiens somehow missed the crash on the diff. The crashes could also be caused by changes to configs or the backend, so would not be captured in the client diffs. And that's why we would find them on master when we didn't find them on the diffs. We also test the alpha release so that we can boost the signal coming from real users so that Sapiens can maybe find more actions. You would have the videos for those. It would make it easier to debug. So this is the current process. As we talked about before, the course of action when you find a crash on a diff is very clear. We comment on the diff and then the engineers fix the crash. But what do we do with the crashes we find on master? We could find many of them, and it might not be feasible to fix all of them before releasing the app to alpha. And there's many situations where maybe it's not necessary to fix these crashes. So for example, some of these crashes that Sapiens finds can be very rare and only happen in specific circumstances with very long sequences of steps that are unlikely to happen with real users. This could be also due to a transient issue or something that only happens in emulators. And also there could be real crashes, but they're very low firing and they're pre-existing, and maybe we don't want to prioritize fixing them. There are some crashes that might only happen to test users, because with test users, we don't have realistic content. We're creating users that are like brand new. They don't have a lot of features or state in them. So they might keep hitting the same crashes that would only affect new users, for example. So a very small percentage of our user base. So the problem that we have here is that Sapiens can find many crashes, but we only know which of these crashes will have the most impact on real users once we actually release the app to real users and see what happens. But our objective is to protect our users from these impactful crashes by identifying them earlier before we release, and then to prioritize fixing them. So the solution we came up with is virtual alpha. Imagine if we have a population of bots that have diverse profiles and where we can release the apps to this population of users. And we can see the same spikes in crashes and find out which crashes would have high impact before any real user is affected. So in a normal release process, we have alpha, beta, and prod. We first release to alpha, and once we feel confident with the quality, we might promote the build to beta for a few days before we release to the entire user population in prod. The problem here is that the crashes we are finding in alpha and in beta are found because real users experience them, and this is what we want to minimize. So virtual alpha sits at the start of this pipeline, and we only need 1 hour to get reliable signal. We release the app to virtual alpha first for 1 hour. We see what we see, and then if there are really high spikes of crashes that are affecting a high percentage of users, then we actually stop the release and fix this crash before we go to alpha. And this way we protect our real users from experiencing those high impact crashes. So what will virtual alpha make possible? Virtual alpha potentially provides many advantages over real alpha. First, we can get signal in under an hour because we control when our virtual users use the app. So as soon as the app is ready, we can make all our users use the app immediately and continuously. We can also control which parts of the app are covered by those users. So for example, we want our virtual users to cover the most popular parts of the app and also new features, and make sure that we are covering all of these things that had changes done to them. We can also simulate conditions in the environment, for example, peak usage of the backend or low memory on the device. These conditions sometimes are don't happen very often when you have a small population of users. So for example, alpha users. So you might, or they might need, for example, peak hours are a couple of hours per day. So you have to kind of at least test for a whole day to make sure that you cover this scenario. But with virtual alpha, we can even simulate these conditions so that we get the signal much quicker. Also, we can have a very good alpha for all our apps and platforms. Some apps don't have enough users on alpha for a specific platform, and this overcomes it because we can have whatever number of users we want for all platforms. Another thing we can do is we can also potentially bisect major issues by releasing different versions of master to virtual alpha to pinpoint the cause of the crash, like what exact point did this crash happen. We can't do this with real users because the quality of master is maybe not good enough to be released to real users, and we might hit other issues other than the issue we're trying to bisect. So it would be very costly to fix all the other issues in all the versions of master. The best way is to just release to virtual alpha, because these virtual users, they're not real users, so there's no danger there. Okay, so let's talk first about this population of bots or test users and what they need to be so that the system is effective. So to be able to create this population automatically and continuously, we created something we call a feature model that represents all the features of the users we care about. For example, number of friends or number of posts. And then the model has the ranges and distributions of these features. For example, for the number of friends, we can say that the number of friends for any user should be between X and Y with a specific distribution based on what we observed in reality. So if you ask the model then for a user spec, it would give you a user with the feature values selected randomly, but based on these ranges and distributions. And then you would get a population of these users that because of this feature model, we can ensure that we create a diverse and meaningful population that, in comparison to traditional test users that have limited state and are all usually the same, is more realistic and hopefully would help us find more real issues and more diverse issues. Okay, so now let's talk about the algorithm and how it can influence the hit rate of crashes in our simulation to make it close to what would happen in production and to pinpoint these high firing crashes that we want to prioritize fixing. So let's go back to the objective. So our objective is to shift left, prioritizing and fixing of regressions that were not found at diff time. So these crashes in master, we want to know which ones of them are more important. So we want to automatically predict which ones are more important so that we can prioritize them and fix them before we release to any real users. So then if we lock down on the algorithm objective, we want the hit rate of crashes found to reflect what would actually happen and how critical they are. So if a crash would be critical in production, we want the hit rate in our virtual alpha to be the same, to be high and flag this crash as an issue. So we came up with a very naive solution. We just want our algorithm to spend time or number of actions at different screens, like different screens of the app, proportional to how popular they are. So let's say, for a hypothetical example, that for the Facebook app, newsfeed is the most popular part of the app, and most of our users spend most of their time in newsfeed. So then in virtual alpha, we want those bots, these test users, to spend most of their time in newsfeed. This can also be a lot more fine-grained. So we can say that, for example, we want them to spend most of their time scrolling newsfeed rather than clicking on different posts in newsfeed and reading them. So we can make this as fine-grained as we like. And this is the solution we came up with. Okay, so if we talk about the virtual alpha testing process, once we have a candidate for release, we would run a number of times, let's say n number of times, which is usually in the thousands, because it's not expensive. They're not real users. They are test users. So you're only limited by the capacity of emulators you have or the machines you have. So let's say that in production, we know that screen 1 is hit 100 times and screen 2 is hit 200 times. So we will have some kind of selection approach that selects the screen to target based on its popularity. And then the output will be a screen to target. This screen to target will be given to the Sapiens screen targeting algorithm. And then we have one run where we're targeting the screen. But if you look at the n number of runs we're running for this build, what we should see is that actually screen 2 is selected 2 times more than 2x times more compared to screen 1, because in production, screen 2 is more popular, 2 times more popular than screen 1. And this way we are spending more time in the more popular parts of the app as discussed. Okay, so once we know which screen we want to target, we give that screen together with the app we want to test and the UI model I talked about before. So when I was explaining the algorithm, I said we build this action graph that tells us about the actions in the UI and how they relate to each other. So we give all this information to the Sapiens screen targeting algorithm, and then Sapiens will come up with a sequence of UI actions that target that screen. So basically, it will give us a flow through the app that makes sure that we hit this screen. Okay, but how does Sapiens know how to reach screen 1? Let's say we chose screen 1. How does it know how to reach screen 1? Let's go back to the algorithm I explained before. So we said that Sapiens will open the app in an emulator, and then it will log in. And then it will start exploring the app, understanding what actions are on the screen, and then putting those actions in a graph and then start building this graph. So let's say we selected one, we went to screen 2. So this is a hypothetical example because like you should have a screen at every point, but it's just to demonstrate the point. So once we clicked 1 and we went, so let's say we saw screen 1. So then we will annotate the graph with screen 1. So that, so if you want to see screen 1, you have to go to action 5 because that's what we saw before. And then we keep building and annotating. And at the end, we will have one graph with all the actions, how they relate to each other. And then also how do we trigger each screen? Which action made us reach which screen so that we know how to reach these screens in the future, right? But this is from one run, and we know that it's almost impossible to cover the whole app in one run. So what we do is we have hundreds and hundreds of runs. And these runs are when we test master, right? So this is like a model building phase of the algorithm. We're building the model, we're trying to learn the app and how it is constructed and how the different actions in the app relate to each other and how they relate to the different screens so that we have a map that tells us how to get to each screen. So let's say we had several runs, like here on the left side, you see that there's 3 different graphs. We would probably have hundreds or thousands of graphs. And then we would just, once a day, we would combine all these graphs and come up with a big graph that tells us all the information we learned over all these runs. So also, one thing to keep in mind is that most apps are not deterministic. It's not like you start, every time you follow a certain path, you will see the same things. There's a lot of randomness. There's things that are based on different circumstances in the back end, in what's trending, and different conditions that the user itself and what type of user they are, they might see different content. So that's why when we combine the graphs, we will have probabilities. It's not always, you don't always, when you go from action 1 to 2, you don't always, when you click on action 1, you don't always see action 2. There's a probability associated with that. So when we combine the different graphs, we also add the probabilities based on what we observed on these edges. And then you have a probabilistic model that tells you how all the actions are related to each other and how the screens are discovered across these actions, with also probabilities on the edges. So you know which different paths are more likely or less likely to lead you to a specific point. Okay, so if we now we have this model and we have which screen we want to target, and we have the app under test, like we said before, and we start to run from Sapiens. Now it's different. We will open the app and then we will look at the actions on the screen. But before we do anything, we will look at our graph. We know that we want to target screen 1. So we will calculate the path that will help us target screen 1. And here on the right, you see that it's highlighted in red. So what we will do is we will select the most probable path to screen 1. So we look at the number of steps, we look at the probabilities, and then we calculate the most probable path. We also add an element of randomness there so that we don't always follow the same path and we don't miss other paths that might lead to different types of crashes. But of course, the most probable path would be the most highly selected. So we will start executing those actions one by one. So now we know the path we know the screen we want to go to, and we know the path we want to take. We start executing action 1, action 2, action 3 until we hit the target. Once we hit the target, we're done. We might select another target with the same approach and go through another path, or we might just want to spend time on screen 1 so that we are doing things on screen 1. So there's one, sometimes like at every point in the path, we might reach a point where we can't find the next action because of like I said, because of like maybe something changed in the app since then. Although we do our model building quite frequently, we do it on a daily basis. Sometimes maybe something changed from like just in that day so that the path is not the same, or you have new alternative paths available, or it could be just that we never covered this new condition. So in that case, what we will do is we will just adapt and adjust. So we will recalculate the path now based on the new information, and then keep following the path. From our experience, this has been very successful. It's not 100% hit rate of the target. So once you select a target, you don't always hit the target, especially for the lower, because you're not just covering the most popular parts of the app, you're trying to cover all parts of the app, but with different distributions, right? So even if something is not popular, you want to cover it at least once or twice, or like 1% of the time. So we found that in some cases, our hit rate is very high, and it's very easy to hit the screen that we are targeting. And in some cases, it's a little bit lower, so then it becomes a little bit more challenging. But overall, our hit rate is good, and it's more than 50% overall, like taking into account all the easy to target and hard to target parts of the app. Okay, so this is the way we run. And because we run n number of times, and this n is in thousands, you then have time spent on each screen proportional to how popular they are in production. Because like, let's say you have 10,000 runs, and let's say newsfeed is where 50% of the time is spent, then you targeted it 50 times and 50% of the time, and you hit it, let's say 100% of the time or 70% of the time because it's easy to hit, then you spent this much time in this popular part of the app. And we found from our experiments on the Facebook apps that this was very successful, and it did lead to crash distribution that is very realistic, at least for the most impactful crashes. So another thing is that, so we are working with different apps. So to begin with, we worked with Facebook on Android, and then we also worked with Messenger on Android, and then we worked with Facebook on iOS. And we found that different apps could have different criteria to why they would want to stop the release. So like we said, if we found issues in virtual alpha, the outcome is that you want to stop the release. You want to say that, okay, don't release this to real users, fix this crash first and then release it. So you'd have an automated signal that says don't release. But the criteria is different for different apps. So while some apps might care about the number of users that are affected by the crash, so even in our virtual population, so the number of users in our virtual population, some would care about the percentage of users, some would care also about the hit rate. Maybe you care if the crash is new or pre-existing. Maybe you care about maybe you care about which part of the app it's happening in. Maybe you don't want it, even if something has a very low hit rate, but it's in, let's say, your most popular screen, you still don't want to release the app, or the opposite. If something has a very high hit rate, but it's in a part of your app that no one uses, then maybe you don't want to stop the release. So the conditions and how they're used is also very configurable, and you can add any conditions you want to that, so that it's custom and it fits the what the app needs, the specific app and its users, and how its release engineers are dealing with the release process, that it fits with that perfectly. Thank you very much for listening. Thank you for your attention. I'm always very happy to come and present at TEQnation, and I hope you found this useful. And it's still early days for us, and there's a lot more detail about this process that we want to release in the future. But I wanted to share this with you and see what your feedback is, and hopefully you have some questions or comments that can help us improve. Thanks again, and I'm happy to take any questions.